So far, we've seen the effect of a magnetic field on individual moving charges. We've seen that magnetic forces always point at right angles to both the magnetic field and the velocity of the charged objects. Magnetic fields cause individual charges to move in uniform circular motion. Earlier this semester, we looked at electric circuits. Circuits produce currents, a sustained flow of electrons through wires and other circuit elements. And these currents can be influenced by magnetic fields as well, because a current is just a set of moving charges. In this video, we will explore two ways in which current-carrying wires respond to magnetic fields. In circuits, the electrons start at the negative terminal of the battery and travel through the wiring to reach the positive terminal. In this animation, the electrons travel through a conductive plate midway through the circuit. The way this circuit is oriented, the electrons are traveling in the positive z direction as they travel through the conductive plate. That is the direction of their velocity. Now, let's see what happens when a magnet is placed around the plate. The magnetic field is pointed in the positive y direction. According to the right-hand rule, and try this out yourself, if the velocity is in positive z and the magnetic field is in positive y, then v cross b is in negative x. Remember that the magnetic force equals charge, Q, times v cross b. Here, the charge is negative, so the force will point in the opposite direction of v cross b, that is, positive x. We saw this in lesson 2. For the electrons moving through the plate, that means that they will be pushed in the positive x direction. This type of warping of electric currents in a magnetic field is known as the Hall effect. Now, since the electrons get pushed sideways to one side of the plate, an imbalance of charge results within the plate, and that imbalance of charge in turn means that there is an electric field within the plate and consequently a voltage drop. In fact, we can calculate the voltage drop as follows. The voltage equals the strength of the magnetic field, B, times the width of the plate, L, times the velocity of the charges, V. The width of the plate is measured in the direction that the electrons got pushed, so in this case, the x direction. For example, if the magnetic field has a strength of 0.02 Tesla, and the width of the wire is 0.003 meters, and the velocity of the electrons is 5,000 meters per second, the voltage drop will be 0.3 volts. The Hall effect has many practical applications. It is used to measure very small magnetic fields in many places, including the disk drives in our computers. It also plays a major role in quantum physics. Magnetic fields don't just alter the paths of electrons in wires, they can also exert forces on the wires themselves. Consider this animation. Here we see a conventional circuit with one segment of the wire suspended between two supports. Let's say the length of that segment is 0.1 meters. As before, the electrons travel from the negative terminal of the battery to the positive terminal. However, remember that by convention, the direction of current is opposite the flow of electrons. In this animation, we're seeing the direction of flow of the current. The length of the wire can be treated as a vector. Its direction is given by the direction of the current. In this case, the direction of the current is negative z or negative k. So we can say that the length of the wire is negative 0.1 k meters. Now, let's place a magnet in the setup such that the prongs of the magnet are on either side of the suspended wire. Let's say that the strength of this magnetic field is 0.06 Tesla. Given the orientation of the prongs, north on the bottom, south on top, the magnetic field points upwards in the positive y direction. So the magnetic field vector is 0.06 J Teslas. Now let's switch on the circuit. Let's say the current is 3 amps. The suspended wire is pushed outward. We can explain this effect by returning to the equation for magnetic force. This original version of the equation applies to individual charges. We can alter it slightly so it is suitable for electric currents. I won't go through the full derivation, but it's not difficult to do. We just need to remember that the velocity of electrons is simply the length of the suspended wire divided by the time required for the electrons to travel through it. Rewriting, we can divide the charge by the time instead to yield current. That gives us the equation at the bottom. We always do the step in the parentheses first. Take the cross product of the length of the wire and the magnetic field. Then multiply the current by that cross product. This tells us the force on the wire. So this is the equation of the magnetic force on a current carrying wire. Let's apply it to the example in our animation. First, we need to calculate L cross B. The size of the cross product is 0.006 Tesla meters. The direction of the cross product is given by the right-hand rule. Try it for yourself. Your hand points in the direction of the length. Your fingers curl in the direction of the B field. Your thumb points in the direction of the force. That's positive x. So we can write the overall cross product as 0.006 I Tesla meters. The force on the wire is then calculated by taking the current, 3 amps, and multiplying it by the cross product, 0.006 I Tesla meters. That works out to a force of 0.018 newtons in the I direction. So in conclusion, the wire gets pushed in the positive x direction by a force of 0.018 newtons. In this video, we have seen 2 ways in which magnetic fields affect electric currents. First, through the Hall effect, pushing individual electrons to one side of the wire and creating a voltage in the wire that is perpendicular to the direction of motion of the electrons. Second, by exerting a force on the wire itself, causing the wire to physically move. In the next video, we'll talk not about how current-carrying wires respond to magnetic fields, but how they generate them.